everyone. We'll do another example of Lagrange multipliers. In this case, we want to find the maximum volume of a rectangular box that can be inscribed inside this surface, so this ellipsoid, where the faces are parallel to the coordinate axes. So what do we have? Well, since we're imagining a rectangular box sitting inside here with faces parallel to the coordinate axes, it means the box is really determined by a point that it's going to sort of hit out here. Because once I know what point, let me just draw the rest of the reference points here. So there's got this point out here on the surface, project it down to the plane. Now that's going to really determine the rest of the box because of symmetry. We're going to go out here, we're going to get another point, we're going to get another point over there, another point over here, and then there's going to be also a point down here, and then we'll sort of connect them all up. It'll be these things all connected together, and so on around the corresponding box like that. So I don't know why I drew that last line in there, but something like this. So there's going to be our rectangular box. So it really all depends on just the coordinates of a point x, y, and z sitting on the surface, because then we just extend it out by symmetry. So what does that mean? Well, it means that the volume of such a box is going to be given by the length times the width times the height. But this will be, since x coordinate and negative x coordinates are going to give us sort of the length. The length is going to be 2x. Then we get a height, or a width of 2y and a height of 2z. And so we get a volume of 8x, y, z. We want to find the maximum volume. So this is the function we want to maximize. So I'll make sure I emphasize that this is a function. It's v of x, y, z. So we want to maximize v subject to the constraint g of x, y, z is equal to, well, these points have to live on the surface of the ellipsoid. So that's our constraint. 4 squared plus z squared over 5 squared minus 1 is equal to 0. That's our constraint. So let's go ahead and write down what our equations are. So we're going to have that the x derivative of v, it's got to be lambda times gx. The y derivative, so lambda times gy. The z derivative is lambda times gz. And we've got our constraint, x squared over 3 squared plus y squared over 4 squared plus z squared over 5 squared is equal to 1. So let's fill out these things. What is v sub x? Well, that would be 8yz is equal to lambda times the x derivative of g. So that's lambda times the x derivative of g. Well, there's a 2 that's going to come out, so I'll slide that in front of the lambda. 2 lambda x over 9 in this case. Similarly for the next one, 8xz is equal to 2 lambda y over 4 squared, and 8xy is equal to 2 lambda z over 5 squared. So it's these 3 equations plus the constraint that we're going to try to solve. 4 equations, 4 unknowns. How are we going to solve these? Well, one way to do this is to notice that we've got 8yz, 8xz, 8xy as the left-hand side for all of these equations, so I can scale them through to make them all equal. So I could go at like an 8xyz is equal to 2 lambda x squared over 9. And then we get an x, y, z is equal to 2 lambda y squared over 4 squared. And an 8x, y, z is equal to 2 lambda z squared over 5 squared. So we get these three equations. And the nice thing about this is they're all equal to each other. Yes, I mean, they're all equal to the left-hand side of 8x, y, z. But even more so, I can exploit the constraint by realizing that if I sum all of these, well, actually, before I sum them, I should divide by 2. I see an extra factor of 2. So I'll factor out by 2, lambda x squared over 9. Maybe I'll write that as a 3 squared. Means the same thing, but it might make the next step easier to see. 4xyz is equal to 2 lambda, oh, the 2's gone because I just divided by it, lambda y squared over 4 squared, and a 4xyz is equal to lambda z squared over 5 squared. And now here is where we notice that I've got an x squared over 3 squared, y squared over 4 squared, z squared over 5 squared on the right-hand side. All the left-hand sides are equal to each other. So if I sum them, so sum the three equations. So I'm just going to add them all together. And what I'll get is a 12xyz on the left. And then on the right, I get lambda times x squared over 3 squared plus y squared over 4 squared plus z squared over 5 squared. But that's equal to 1. That's the constraint. So summing these equations boils it down to just this nice, straightforward equation. So there we go. There's a new equation that we have relating all of them. Now, what can I do with this? Well, what I'll do is I will plug into, which one do I want to plug it into? Well, I can actually plug it into any of them because that's an expression for lambda. It allows me to get rid of lambda. So I will plug it into, I'll call this equation 1 here. So I'll plug it into equation 1. And I will indicate that when we do that, what I get is 4xyz is equal to 12xyz, that's lambda, times x squared over 3 squared. And so I get these xyz's all cancel. I have to be careful that we can really cancel those things off. Might need to worry about, can x be 0? Well, if x is 0, then what happens? Well, if x is 0, then the volume is 0. And if y is 0, the volume is 0. If z is 0, the volume is 0. We're trying to maximize the volume. And so we know that we're going to get some positive volume. So we're not going to worry about the case where the volume is 0 because that's not going to be the maximum. So that's why I'm canceling these things off, because I can assume x, y, and z are positive. I can assume they're positive. I'm assuming they're in quadrant 1 or octant 1. Okay, so then this becomes, well, the 4 and the 12, they got a common factor of 4. So I get 1 is equal to 3x squared over 3 squared. Or in other words, x squared is equal to 3 squared over 3. Or in other words, x is equal to 3 over root 3. So there is my x value. You might say, well, how come you're ignoring negative values and the like? Because my first thought was, I'm just going to be looking at one vertex. Because of symmetry, I can get all the other ones. So I look at the octant 1 vertex, and that's going to be with positive x, y, and z values. So there we go. We plugged into 1, we got an x value. Then we can just do the same thing for plugging into 2 and 3. So maybe I'll call this equation 2 now. So plugging it into 2, we get that 4xyz is equal to lambda, which is now 12xyz, is multiplied by y squared over 4 squared. So I'll clean that up a little bit. So that's plugging it into the second equation. And again, we get 1 is equal to 3 times y squared over 4 squared, or y is equal to 4 over root 3. And we can do the same thing. Plug into equation 3, and we get that 4xyz is equal to 12xyz, z squared over 5 squared. And that gives us that same argument, z is equal to 5 over root 3. And so we found our point. Therefore, x, y, z, the dimensions of that box are 3 over root 3, 4 over root 3, and 5 over root 3. And the volume then is given by 8 times 3 over root 3, 4 over root 3, 5 over root 3, which is 8. And so we got 20 times 3 is 60 times 8 is, we could multiply these things out, or we can just write it as 8 times 3 times 4 times 5 all over 3 root 3, whatever that works out to be in the end. We could simplify this a little bit. I can see a cancellations of a 3 here. And then therefore, I've got a 4 times 5, which is a 20, times an 8 is 160 over root 3. Okay, so we'll leave it like that. There we go. There's our volume. We were asked to maximize. Do we know that this is a maximum volume? Well, we know this is an extreme case. It's an extremal answer. So it's either a maximum or a minimum. But we also know that we can make the volume as small as we want just by making this rectangle as tiny as we want. Rectangle as tiny as I want means that I could take my x, y, z value in such a way that this becomes a really sort of pencil-like rectangular box, opening just right along the y-axis. Very, very small in some sense, tiny volume. So the volume can be made as small as I want. So it means that what I have found here is, as an extremal case, it's the maximum. So this is the maximum value. Maximum volume. All right, that's it for this example.